Hey everyone, today I will do a Bitcoin price prediction by using a baseline model with Prophet. And as to the short introduction of Prophet, the mathematical equation behind Prophet model is defined as this: yt equal to gt plus st plus ht plus et, where gt represents a trend component. Prophet uses by default the piecewise linear model for trend forecasting. St represents the seasonality component, which can be periodic changes, for example weekly, monthly or yearly, and the ht represents the effect of holidays, and lastly the error term, that is the et. And Prophet model fitting procedure is usually very fast, even for thousands and thousands of observations, and it does not require any data pre-processing. It deals also with missing data and outliers, and that's the main benefit of Prophet. And for the dataset source, I have put the link here. It's very much available in Kaggle, and I will also put the link in the description of this video. And if I read the dataset with pandas, this is as simple as this. I have the date column, and then the Bitcoin prices, total volume, market cap, and coin name. Of course, here all of them are Bitcoin because I'm only focused on Bitcoin in this exercise. And if I print a shape, it's 3036 rows, and actually these are daily data. So each data point, each row represents one single day. Remember that. And whole data starts from it is up to actually 2023 0424 24th April, and it starts from, if I put the head here, did I print head? Okay, let's just print the head here. PC dot. Right, it starts from 2015-0101, so the entire trading market of Bitcoin. Alright, and then with btc.info you have the information about the whole data frame. So I have 3036 entries here, and the date column here is an object. I need that to be of date time. Price as I needed, it's in float 64. And alright, so now btc.isnull.sum gives me there is no null values except one value in market cap, but I'm not going to use market cap column for this exercise. Now next, convert the date column from object to date time. So you just implement bd.toDateTime method here and pass your date column. And then another quick thing, actually I did not do this, so that's why it is commented out. So just in case, if you want your model to start from a particular date, for example maybe somewhere in between the entire time frame, then you can do just this. Just locate only those dates which are ahead of a particular date. So in case if I wanted my data to start from 2019-0101, I can just extract only those dates which is more or equal to the start date. But here, for the purpose of this exercise, I'm taking the entire data set for training. And yeah, btc.shape will give you 3036 rows and 5 columns. And then as required by the Prophet model, I need my date column to be named DS and price column, that is a target column, Y. This is a requirement of the Prophet package, and so I'm renaming those column here. And after that renaming, when I do btc.head, I get those renamed data frame. And then the important augmented Dickey-Fuller test. It's a time series exercise, so you need to do the check for stationarity. And the time series is said to be stationary if it has no trend, exhibits constant variance over time, and has a constant autocorrelation structure over time. And one way to test whether a time series is stationary is to perform an augmented Dickey-Fuller test, which uses the following null and alternative hypothesis here. So here the null hypothesis H0 is that the time series is not stationary. In other words, it has some time dependent structure and does not have constant variance over time, or series has a unit root. And the alternative hypothesis HA here is that the time series is stationary, or the series has no unit root. And as per the theory of this ADF test, if the p-value from the test is less than some significance level, for example alpha equal to 0.05 or 5%, then we can reject the null hypothesis and conclude that the time series is stationary, or that the series has no unit root. Now, in probability theory and statistics, a unit root is a feature of some stochastic process such as random walks that can cause problems in statistical inference involving time series models. In simple terms, the unit root is non-stationary but does not always have a trend component. And if the null hypothesis is failed or rejected, this test may provide evidence that the series is not stationary. Now, for the condition to reject the null hypothesis, that is H0, is that if the test statistic is less than critical value and p-value is less than 0.05, then reject null hypothesis, that is time series does not have a unit root, meaning it is stationary. And it does not have a time-dependent structure. So we are going to check exactly that with this simple line of code. So I'm going to import this add Fuller test from stats model, and then you define your BTC price vol, this variable, to be the data frame taking only the target Y column and the total volume, and then you do your test with these few lines. And here you just initiate an instance of add Fuller, and as a first argument you pass your BTC price vol.y.values, that is all the target values. And then I'm just printing from the result, I'm just printing the 0th element and the 1 index element, and also printing the key and value of the result 4.items. And from this you get the ADF statistics of this value, p-value of 0.49, and then some of the critical values. So my critical values, 1% as -3, critical value 5% -2, 10% -2.56. And now as to the interpretation, actually before the interpretation, let's quickly go through these variables. The ADF statistic, this value represent the test statistic used to compare with the critical values to determine if the time series has a unit root or not. And the p-value, this value indicates the probability of observing a test statistic as extreme as the one obtained if the null hypothesis were true. In general, if the p-value is less than 0.05, we reject the null hypothesis. And we have 3 critical values here, 1%, 5%, and 10%. So these are the critical values of the test statistic at different significance level, which is 1%, 5%, and 10% respectively. Here we compare the ADF test statistic with these critical values to determine whether to reject the null hypothesis or not. And in this case, the ADF test statistic is 1 minus 1.5835 and so on, which is greater than all critical values. And also the p-value right here, this one is 0.4918, which is again greater than the common significance level of 0.05. So based on these findings, we fail to reject the null hypothesis. This means that we do not have enough evidence to conclude that the time series is stationary. In other words, the time series likely has a unit root and it is non-stationary. Now, to make the series stationary, you can try differencing the series, applying a transformation, for example, logarithmic, or using seasonal decomposition. After applying any of those techniques, you can perform the ADF test again to check if the modified series is stationary or not. But in this case, I'm not going to make that series stationary by doing those transformation. And part of the reason for that is that I'm using fbprophet here as my tool. So the question is, does the input data need to be stationary to forecast with Prophet? And the answer is no. Stationarity is an important condition for some other time series forecasting algorithm such as ARMA or ARIMA, but Prophet assumes nothing about stationarity. So you don't need to make your data stationary before you feed them into the Prophet library. Prophet rather makes use of features like trend or seasonality, which stationary data by definition do not have. So if you feed stationary data into Prophet, the forecast result most likely would be close to a flat line. And we could say that forecasting with such stationary data is not actually the area for application of Prophet. Hence, we go ahead modeling with Prophet. In this line, I am initiating an instance of Prophet, then model.fit, and to that you pass your main data frame. and then you create future data. So for that you need to make use of these inbuilt function of prophet make future data frame, periods equal to 2, frequency equal to m, which means I'm creating next 2 months of data on which the prophet will predict. And for the prediction, just a single line, model.predict, and you pass your future data frame. And that's it. Actually, this training with Prophet is so easy. It just 3 or 4 lines of code. And then you just plot your prediction with this model.plot and pass your forecast. And that will have this plot. And I also want to see the various components of the prediction, because we know that Prophet within it has 3 components, which are the base trend, the seasonality, and holidays. And we have not dealt with holidays specifically in this exercise. So to plot the components, use another built-in method of Prophet, which is plot components. And again, just pass your forecast. And with this single line, you will have this nice plotting right here, which will have the first plot for trend, then for seasonality. And we can see the trend here. It is very much recognizable. From late 2020, Bitcoin went through a huge price rise, and then from late 2021, it is continually coming down. And for the weekly trend, we can see this seasonality. So as we can see on the at the end of Friday, it is always hitting almost the lowest price. So it's you can interpret this that this point is a nice point to take your buy position. All right, now this plot and the prediction that we just completed, it was based on linear growth. And I did not have to specifically mention the linear growth because Facebook Prophet by default takes a linear growth. Now next, I want to train the same model with logistic growth, and the logistic growth model is more suitable for cases where the growth of the series is expected to slow down as it approaches a certain limit. In our case, we will fix the carrying capacity, that is this value right here, to be a constant value because the price last year towards the end was slightly increasing. And the carrying capacity is usually just some maximum achievable point. The important things about carrying capacity are that it can be specified for every row in the data frame, or it can also be a constant value, which is what I'm choosing here. And the rest of the code lines are pretty much actually the same. You create an instance of Prophet, only difference is you pass your growth to be logistic here. And then make a future data frame for the next 2 months. That is, I'm passing the frequency M and periods too. Create your forecast by doing model logistic.predict, and then again you plot the forecasted model. And here is that plot of yours from the forecast data. And I'm also just previously I'm plotting the components with plot component method. And so that's my trend with logistic, and otherwise for the weekly as well, the trend I can see the seasonality at the end of Friday, the price is always touching the bottom. All right, so now let's move ahead. All right, till now we were forecasting using Prophet by creating a future dataset with the use of the built-in method make future data frame. And now what I want to do is forecast by splitting my original data into train and test. So what I'm going to do is define a split date, which I'm defining it to be 24th October 2022. And any dates before this date is my train, and any data after this date is my test set. And I'm extracting that by using this conditional within my data frame and using the locate method of pandas. So now I have 2853 number of rows in my train set and 183 in my test set. And the rest of the steps are almost same. You create an instance of Prophet, you run your model.fit, and then model.predict. And the result of this model.predict is your actual forecast from the Prophet model. And that I'm naming data test forecast. All right, and you can plot that by doing model.plot and passing your data test forecast. And that's your plot. This part is for the forecasted portion. And also you can do the same plot components on your forecasted test set. And that's exactly what this is doing. And from plot components, we can see the trend basically remains the same. That is, for the end part of 2022 up to the beginning of 23, it is a downward trend. And for the weekly seasonality, we can again see Friday end, it's touching the bottom price. And yeah, so now I want to plot the forecast with the actual. And for that, I have two things here. Once I'm passing ax.scatter as my actual ground truth data, which is testdf. And I'm taking only the DS column, which has your dates, and then passing the actual test DFY, which is actual target values. This Y represent here the actual prices of Bitcoins, and these are ground truths. And then another plot with model.plot, and there I'm passing the forecasted data, and this is your forecast. And it looks like the prediction from Prophet is not really matching the ground truth here. And next, I also want to plot a single week, and you can do that by using ax.setxbound. So what I'm doing here, I'm just defining one lower date and one upper date, and I'm making use of dt.datetime and passing my year, month, and date. So I'm just taking the last week of December 2022. And then I'm plotting with with model.plot and ax.scatter. That is, again, ax.scatter will take your ground truth, which is my testdf.ds, that is the dates and the target value y. And this is my forecast model.plot that takes a forecast data frame. And this is the result for a single week. And here I don't see much of divergence. And this is just for a single week. All right, at the end, I just want to calculate the mean absolute error. This metric I have already imported at the very top from sklearn. And to that, you pass your y true, which is your test df and the y column values, and your y pred, which is y hat. It is coming from data test forecast. Because if you print your data test forecast, this is the form it will take. So you can see that it has got a lot of components, a lot of columns in it, a lot of information within your forecast data frame. And this was the result of running model.predict. Remember that. So one of these is this y hat lower, y hat upper, and I am here making use of y hat. So mean absolute error for this particular dataset came out to be 6532, which is not too good really, or not too bad as well, because Bitcoin by its very definition has gone through a huge volatility from its beginning of 2015 data that this exercise was built upon. And because of that extremely high volatile nature of Bitcoin, any forecast of Bitcoin also would have relatively higher mean absolute error, and that's what we are seeing here. Alright, that's a wrap for this video. Stay tuned because I plan to do quite a few interesting projects involving LSTM, XGBoost, and time series over the coming weeks. So thank you very much for watching, and see you in the next one.